Okay, please be seated. We're about to get started.
Yeah, sure.
Okay, so the last but not least is Francesco Benini from CISA. He'll tell us about entanglement, symmetry breaking, and categorical symmetries. So let's welcome.
Can you hear me? Yes, this one. Okay, very good. So, yeah, so I will talk about a couple of papers. One was from last year. One will hopefully appear soon. And this is the collaboration of people involved. Pasquale Calabrese from CISA, probably you know him. Victor Godet, new hire at Jussieu. And then three excellent students, Michele Fossati, Amartya Singh, and Marco Venuti at CISA. They will apply this fall. So keep your attention on it. All right, so we'll talk about symmetries, and in particular, the breaking of symmetries. And so the standard approach to symmetry breaking is so-called Landau paradigm, that is to use local order parameters. The local order parameter is some local operator in the theory, which is charged under the symmetry. And if you have a state and we want to know whether the state breaks the symmetry, we evaluate the expectation value of this operator. And if this expectation value is different from 0, it means that the symmetry is broken by this state. In high energy physics, most often the state is the ground state. We are interested to know whether the ground state preserve the symmetry or break the symmetry. But if you go to many-body physics or statistical physics, excited states are equally interesting, and often they are even more interesting. There is more dynamics. So this is, of course, very well-established framework. However, recently, in the last couple of years, another approach has been put forward, in particular by Ares, Morciano, and Calabrese, which is a quantum information-based approach. This builds on a lot of previous work that was done in the last decade. And there is also similar ideas developed also slightly a few years before by Casini, Huerta, Magan, and Pontello. And so the idea is to construct some observable, some quantity using quantum information methods that can detect symmetry breaking in states. So the quantity that they defined, and I will define precisely this quantity for you in a moment, but let me just give you a teaser. So this quantity, they call it entanglement asymmetry. So this is a number, and it turns out that this number is positive if and only if the symmetry from the point of view of this state is broken. So this quantity is interesting because this is a faithful detector of symmetry breaking, in the sense that the minute that this is positive, you know that the state breaks the symmetry. If you use a local order parameter, this arrow goes in one direction, not in the other one, because it might be that the particular operator that you looked at does not have an expectation value in the state, even though the state breaks the symmetry. So in principle, you have to look at all possible order parameters in order to be sure that the symmetry is broken. Also, this quantity depends on a subsystem, A. So this is in the framework, in the setup of entanglement entropy. And so there is more dependence in this quantity. We can play with the subsystem. We can study whether the symmetry is broken in a subsystem. And we can try to extract physical information by varying the size or the shape of this subsystem. And besides, this technique applies to ground states, but it also applies to excited states. So we can use it in high energy physics to see whether the ground states break the symmetry or not, but you can also study excited states. Okay, so the basic building block is entanglement entropy. Now, many keywords that will appear in this talk also appeared in the previous talk. So that is nice. So various concepts have already been defined. What is entanglement entropy? Most of you are probably familiar with it, but let me just say it anyway. So this is a quantity that, given a certain quantum states that I can call rho full, state of the full system, measures how much the degrees of freedom in a subsystem that we call A are entangled with the rest of the system that I can call B. The typical setup is that there is a full Hilbert space of the system. We assume that this factorizes into a Hilbert space of the subsystem and of the complement. For instance, we might be dealing with a spin chain, and then we take a subset of the sites. This will give the Hilbert space of the subsystem, and then the other sites give you the other part. And then we take a state. It could be a pure state, and then we construct the density matrix, or it could be a mixed states. We compute the reduced density matrix for the subsystem, and then we compute the von Neumann entropy. So this is the definition of entanglement entropy. Okay, just for notation, in the following, I will not write rho A every time. I will just write rho, but rho is the reduced density matrix of the subsystem. Now, this definition works perfectly well in quantum mechanics. It can also be extended to quantum field theory. There are lots of subtleties because there are divergences that have to be regularized, but all of this can be done. And so it can be extended to quantum field theory, which is the setup that I will be interested in. And typically in quantum field theory, the subsystem is some spatial subregion. This is not the only possibility, but this is the typical setup. Okay, so now suppose that the system has some symmetry. And to begin with, consider the very simple and basic case that the symmetry is a U1 and there is some charge. Okay, this is the basic setup that was considered in this initial paper on this quantity. So suppose that the charge can be factorized as well. Essentially, you integrate the current on the subsystem, and here you integrate it on the complement. Now, obviously, the symmetry is broken in the subsystem if and only if the charge that acts on the subsystem commutes with the density matrix. Okay? So now we would like to, or they wanted to construct a quantity that can detect when this happens. Okay, some number that I can quantify when this happens. And so here it is their idea. So you take the reduced density matrix and you construct a symmetrized density matrix. So essentially you average over the action of the group. You see this thing here is the action of the U1 on the subsystem. You take the exponential of the charge with some parameter alpha. You do it on both sides because rho is an operator. So this is the natural action of U1, is the joint action on operators. And you integrate over the group. This parameter alpha is the parameter of U1. So this gives you an average or symmetrized density matrix. Now, it turns out that in the abelian case, you can rewrite this in some nice way, which is written here. So since we have a U1 symmetry, there are charge sectors. And we can construct the projector on the Hilbert space on a given charge sector. And what you do is that you project this density matrix on a given charge sector, and then you take the sum over all charge sectors. So pictorially, if this rho, you write it in this basis in which each block corresponds to a fixed charge, a generic reduced density matrix will occupy all the blocks, and this symmetrized density matrix only contains the elements along the blocks that are along the diagonal. Okay, you just set to 0 everything which is off diagonal. Yeah, the asterisk represents generic elements. So rho is completely general, and what this operation does is that it sets to 0 everything in the light blue region and keeps everything which is in this yellow region. This is true for the abelian case. In the non-abelian case, is more complicated. I mean, it's not more complicated, it's just that here you further have a projection on the identity. And then only the first line works, the second line is not equal. I mean, you cannot write in this way. Okay, so you start with you have your reduced density matrix, you construct a symmetrized density matrix, and then you want to compare the two. And of course, you can define various measures of the difference between these two matrices. They define this quantity that they call entanglement asymmetry. You compute the difference of the von Neumann entropies of the two matrices. And it turns out this is something special because this is a projection. It turns out that this is equivalent to the relative entropy between the two matrices. And the relative entropy was already introduced in the previous talk. So it's this formula in which you have rho log rho minus rho log rho q. Okay, so you use this as a measure of the difference between the two matrices. And this is a very nice measure. Of course, it's not the only one, but it's nice because of the following reasons. First of all, it is non-negative definite. This is a general property of relative entropy. And besides, if it is zero, if and only if the two matrices are equal, and the two matrices are equal if and only if the charge commutes with the matrix. So the minute, as I said before, the minute that this quantity is positive, you know that your reduced density matrix does not commute with the charge, and so the symmetry is broken. Yeah. Is it? Yes, yes. So it turns out that rho q is itself a density matrix. So the trace is equal to 1, and it is positive. And yes, I mean, I will, in the second part of the talk, I will have a more general framework. But yes, you can easily prove it from the definition before. Well, I mean, this is in the abelian case, and I mean, it is true. You can prove it. You have to assume certain facts about. I mean, for U1, this is just true. In the general case, you have to assume a few facts that you have a sister algebra, but it's true. Okay, maybe for a simple proof, I can think about it and we can talk afterwards, but it is true. All right, so this is the first property, which is nice. The second property is that in this definition, I never use the Hamiltonian. So this only depends on the state, which means that one could use it also to describe explicit breaking of a symmetry. So you could have a theory, and maybe you add some terms to the Lagrange, and you have explicit breaking, and you want to know what is the effect on the ground state. You can do it, okay? Because the Hamiltonian never enters in this definition. However, if the symmetry is spontaneously broken, or if it is explicitly broken by in a soft way, that means you only break it into the infrared, then you see that since you take a difference between two von Neumann entropies, the divergences come from the UV, so the divergence will cancel, and this quantity is well defined, doesn't have divergences that you have to regulate, is already well defined. Yes? Yeah, so as I said, there are different questions that you can ask. So you can take the ground state. And if you take the ground state, of course, you want to have symmetry breaking. You want to go into the thermodynamic limit. Or you could consider an excited state. And you want to quantify how these excited states break a symmetry. And then maybe you can ask other questions. Because there is no problem for an excited state to break the symmetry, right? I mean, a state in general is not invariant under the symmetry. No, you have a state, you act with the symmetry, and you obtain another state. As I said, this is not the typical question that we ask in high energy physics, but in statistical physics, it's quite normal. So you can think of a quench, for instance. No, you do some quench, you create some state, and you might ask whether the states break or not the symmetry. Okay, so now this quantity is hard in general to compute because you have to compute the log of a density matrix. And of course, in quantum field theory, this density matrix is infinite dimensional. And so there are other quantities more easy to compute. They are called Rényi entropies or Rényi asymmetries, in which you compute the trace of an integer power of the density matrix, and then you take the log. And then, if you are able to analytically continue this quantity to complex n, then you can take the limit n to 1, and you can recover the von Neumann version. However, it turns out that these Renyi asymmetries also share similar properties. They are non-negative definite, and they are zero if and only if the matrix commute. And so one can use these quantities as well. So these are also interesting to study. All right, so this quantity has been defined relatively recently, but there's been a lot of activity. So this asymmetry has been computed in a variety of quantum systems. Typically, these are 1D or 2D systems, like spin chains, free fermions in 2 dimensions, integrable systems, other systems that I'm not very familiar with, like matrix polar states, random quantum circuits, systems that are studied a lot, as I say, in the context of many-body or statistical physics. Often these computations are numerical. And so before going into our work, I would like to highlight some few selected results, interesting results that have been obtained. So of course, from the point of view of high energy physics, as I say, the very natural question is, what are the properties of the vacuum? And so if you take the vacuum, you can compute this quantity. And if you have a discrete, actually, if you have a finite symmetry, and this finite symmetry G, for some finite group G, is broken to H, then this quantity turns out to be the log of the order of G divided by the order of H. So essentially, this is the log of the number of states, like you would expect from a von Neumann entropy. So in a sense, if you can compute it, you can measure whether the ground state breaks a finite symmetry or not. Yeah, so this is generic finite group. I don't know what. Oh, in general, yes. So the proof that was done in this paper uses these matrix product states, which are in 2 dimensions, but you can rephrase the proof using a topological field theory, then it applies in any dimension. They didn't do it, but it's easy to do. So yeah, so here I'm assuming that the system is gapped. So this is for you spontaneously break a finite symmetry, you assume that the system is gapped. This is the result. If you have the breaking of a continuous symmetry, this has been computed in 2 dimensions. Then, of course, it's not symmetry breaking, and in higher dimension has not been computed. So I don't know for symmetry breaking what one should get. Say again? Yeah, so here, if you want, this is the infrared result. So if you have the full theory, this is valid in the limit in which the subsystem size goes to infinity. Because they say you can derive it using the topological field theory, which is the low energy description, the very low energy description of the system. Otherwise, yes, it's not, it's not an equality. It's much more complicated function as you change the size. Yes, thanks. Another interesting result is a quantum version of the so-called Mpemba effect. So the Mpemba effect is a very interesting classical phenomenon, which is the fact that hot water freezes more quickly than cold water. Okay, this is very unintuitive phenomenon. It was already observed by Aristotle many years ago. He said that if you want to freeze water, start putting it into the sun. And of course, it's an out of equilibrium effect. It's an effect which is not understood very well in the sense that there are so many variables in the game. It's not clear which variables and which properties control it, in particular when this happens and when it doesn't happen. There is a very nice story about this Mbempa that was a high school kid and how this came out. I can tell you afterwards. But anyway, this group, again, the group of Calabrese, devised or observed a sort of quantum version of this Mpemba effect. In fact, quantum version have been discussed also before. This is a sort of quantum version in closed quantum systems. So I will not describe these pictures in full detail now. If you want, this is a teaser. I will describe it more in the context of our work. So we'll come back to it. But let me just say that this has also been experimentally measured, because it turns out that the Renyi asymmetries can be experimentally measured. And so they did the experiment in 24, and as you see, the experiment matches very nicely. So this quantity is even experimentally measurable. Sorry? Yeah, so I mean, I should explain what is this. So essentially they take a spin chain, a ferromagnetic spin chain, and theta is, so they consider a U1, which is the rotation of the spin, and theta is the angle. So they take a state in which the magnetization is not along the direction of the U1, but is an angle. So if you want larger theta, corresponds to more breaking of the symmetry. If you want theta equal to 0, means that your state is aligned, doesn't break the symmetry. As you increase theta, from the green curve to the red curve, there is more breaking of the symmetry. So because it's more disaligned. And so, okay, so what they observe is that if you break more the symmetry, then more quickly you relax and you recover the symmetry. So this is the sort of quantum version of essentially the crossing of these lines is the hallmark of this quantum version of the Mpemba effect. All right. And then one last interesting result, perhaps especially for this section of the conference, is a sort of page curve of entanglement mass symmetry. So again, it's the same group of people. What they did was to take the page model of a black hole, this model in which you take a bunch of spins, and you take a randomized state in this bunch of spins. So this is a very, very crude model of a black hole. And then you model evaporation as the fact that you consider a smaller and smaller subsystem, a reduced black hole, and the complement is radiation. And they computed the asymmetry of the complement, and they obtained these curves. So here the red curve is the large n limit, while the other two curves are finite n. So let's look at the large n. And as you see, up to for a certain time, this asymmetry is 0, and then there is a jump, there is a sort of phase transition, and then it is non-zero. So yeah, as I say, you can call it some sort of page cover entanglement asymmetry, and I think it's an interesting question to understand what physics is describing and if it can be reproduced from gravity. All right, but if you have questions, feel free to ask. Okay, so as I said, the examples that had been computed in the literature, especially in the statistical physics community, are mainly 1D and 2D systems. So what we did was to try to see what happens in higher dimensions, in particular starting with conformal field theories, where there is a lot of control, but going to generic dimensions. Okay, so if you are discussing CFTs, then there is not much to say about the vacuum, because the vacuum doesn't break the symmetry. So the symmetry is 0, there is not much to say. And so we decided to study some excited states. Okay, so what excited states? Of course, there is a very large space of options. And so we studied states that have a Euclidean path integral preparation. Yeah, so from the point of view of Euclidean path integral, these are very natural. So essentially what you do is the following. So if you have a path integral on a half space, this gives you the vacuum. But now let's insert a local operator in the Euclidean path, and this creates some excited state. And in particular, so we can choose some scalar primary V of charge 1 and some dimension delta. And then we can insert the identity plus the primary. Now, why we do that? Because if you only insert the primary, it turns out that this is an eigenstate of the symmetry and doesn't break the symmetry. So you really need to construct a state that doesn't have a well-defined charge, because otherwise it only gets a phase, but a phase is the same state. Okay, you want to move to another state. So you do this is the simplest thing. So you insert it here, and then again, Euclidean path integral allows you to construct the density matrix. You just take another copy, mirrored, in order to construct the conjugated state. So this will be the future Euclidean path integral, and then in order to obtain the reduced density matrix, you glue on the complement of the subsystem, and you're left with a cut along the subsystem. So this red double slit is a cut. Okay, so this is a Euclidean preparation of the density matrix. Moreover, it turns out, yes. Yes. So I'm not writing any sub letter here. So rho for me will be the reduced density matrix. Moreover, as we will see in a moment, it turns out to be very convenient to work in a perturbative limit in which lambda is very small and work at leading order in lambda. We will see why. Let me also say that these states are very natural from the point of view of holography, because in holography, this V will be due to some scalar field in the bulk, and if you turn on boundary conditions for this scalar field, this corresponds to turning on sources and V, right? And if these sources are very small and then they are localized at a point, you precisely create state of this sort. So these states can be easily realized in holography in a limit in which the sources go to zero. And in fact, towards the end, I will discuss some holography, how we can try to describe this in holography. Okay, so how do we compute this asymmetry? So I will show you two methods. One is the replica method that was already discussed before. So this applies to the Rényi asymmetries. Essentially, we have compute trace of some power of this either reduced density matrix or projected density matrix. So how do we construct, what is the Euclidean preparation of this projected density matrix? Well, okay, so first of all, what we have to do is that we have to take copies of this reduced density matrix. We have to insert the action of the group, right, this exponential of alpha q, and then we have to integrate or average over the action of the group. Okay, so this is called the charge moment, and then we have to integrate over alpha. So how do we compute these charge moments with a path integral? Well, again, so we glue the copies. We have these n copies of spacetime. We glue through the cut, as in the standard story. But now we put an operator that implements the action of the symmetry along the cut when we go from one copy to the next. And in fact, these lines here, these are codimension 1 operators that turns out to be topological operators, if you want topologically symmetry defects, that implements the action of the symmetry, as was introduced more than 10 years ago by Gaiotto, Kapustin, Sandberg, and Willett. So this connects with all the story of generalized symmetries. So now we should compute essentially these path integrals in which we have these multiple copies. They are glued. There are the insertion of these lines, and besides, there are the insertion of these local operators that prepare the states. In general, this is very difficult because this is a manifold with singularities. There are branch singularities, and so in general, it's very difficult. If we go to 2 dimensions, then it turns out that this branch covering can be smoothed out by a conformal transformation. So we can do a conformal transformation where there are no singularities any longer. And then we have to compute, we have some other Riemann surface of some genus, and we have to compute a 2n point function, correlation functions. Essentially, there are the 2 insertions, and there are n copies of them, with this extra insertion of these topological operators. And if we have a specific theory, for instance, some minimal models, this can be computed with some work. But of course, in general, I cannot give you a universal result. However, if you look at leading order, and we look only at leading order in lambda, then lambda multiplies the operator. So at leading order, we are only looking at 2-point functions. But now 2-point functions are universal because they are controlled by dimensions. And so in this case, we are able to write down a universal result for this asymmetry. And in fact, for instance, if I take what I will call the Rindler geometry, the geometry in which the subsystem is a half line, half infinite line, then you essentially have to sum some 2-point functions, and if you parameterize with r and some angle theta, some angle tau 0, the position of this insertion, you can write down very explicitly the answer, the leading order in lambda for this asymmetry. The next order, as I say, this will be controlled by 4-point function and 6-point function and so on that do not have a universal expression. Okay, but in specific theory, you can compute them. So this works in 2 dimensions. It turns out that there is a different approach that only works at leading order in lambda, but allows us to go to generic dimension. And this is the fact that this, the entanglement asymmetry, so now I go to the von Neumann version, is a relative entropy. And if we work at leading order in the deformation, so at zeroth order, we have the reduced vacuum. And then at the first order, we deform it with the insertion of these operators. And it turns out that if you study, so people studied relative entropy and the expansion of relative entropy at first order in a perturbation, this turns out to have an integral representation as the so-called Fisher information metric. So there is some integral, this S is a parameter, and you have to compute this trace. So this gives the leading order in lambda. Okay? Further orders are very complicated, but the leading order is simple. It is symmetric, yes. Yes, so this is a metric. If you want, this is a metric on perturbations of a density matrix around sigma. So you take sigma, and yes, this is a good metric for perturbations. Now, in general, this is still a very complicated object. It simplifies, again, I'm using what was already explained in the previous talk. It simplifies when the modular Hamiltonian, which is the log of the density matrix of the vacuum, is local. So in particular, this happens for very simple geometries like the Rindler geometry. Then in this case, this object here reduces to an integrated two-point function. And so once again, this can be computed in general. And this gives a universal answer. The answer is written here. It's not particularly important. What is the function? It's a hypergeometric function. What is important is that there is an explicit answer. This does not depend on the dimension, so this applies in any dimension. But of course, this is only for the leading order in lambda. So okay, so this is the answer for this Rindler geometry when the subspace, so we are when the subspace is a half space. Okay, we are in generic dimension. The subspace is a half space. But then we can use conformal transformation to obtain the result for other type of subsystems. And because these entropies will have fixed transformation laws under conformal transformations. For instance, the von Neumann one at leading order in lambda behaves as a two-point function. And so we can transform it under conformal transformations. And in particular, we can obtain other geometries. So we can obtain a spherical disk in infinite volume. We can obtain a spherical disk in finite volume if the total volume is a sphere. And we can do a spherical disk at positive temperature, but then space is a hyperbolic plane. But if we are in two dimensions, this is the same as the real line. Okay, so these are some geometries that we can discuss. Okay, there is something else that we can do, which is quite interesting. We can again use conformal maps and analytic continuation to obtain the temporal evolution of this entanglement asymmetry. So far what I described was the following. You take some Euclidean part integral, this prepare a state, and compute this entanglement asymmetry. But now we can let it evolve in Lorentzian time with the Hamiltonian of the theory, and we can try to see what happens. Okay? So we can think of this as a sort of quench that produces this state, and then we let it evolve with the Hamiltonian. How do we compute this? Well, it's quite simple. We have to take this slit, this cut, we move it in Euclidean time. When we do that, we no longer have this mirror symmetry between the past and the future. So we are computing the asymmetry of a non-Hermitian density matrix, which is fine. But then we do the analytic continuation. So we go to Lorentzian time, one now is vertical motion. And now this is the Hermitian, this describes the Hermitian density matrix. And so changing the height of this cut, we can obtain the temporal evolution. Yes. What do you mean before they coincide?
Before.
Yes.
Before you had time to
yes.
insert it, coincide with the cut.
Yes.
Doesn't it some singularity?
No. So when you consider only the contribution from the 2-point function, it looks like you get a singularity. But if you include higher point function, so if you have the complete answer in minimal models in 2 dimensions, it turns out that it does not diverge. That diverges. So at second order in lambda, yes. And at that order, it seems to diverge if you take this limit. But if you go to a minimal model, like the easy model, and you take the 4-point function, and you do the Renyi one, because the von Neumann, then I don't know how to do it. And you do the Renyi, those do not diverge. But then I don't know how to do the von Neumann, because I don't know how to compute it for any n and analytically continue. I know how to do the von Neumann only at leading order. I mean, your question points out that you have to be careful, because what you obtain, you have to make sure that what you obtain is valid, because the next terms might change completely the answer. So yeah, thanks for the comment. Okay, so first of all, what do we expect? So of course, the system has a unitary evolution, so this excited state cannot go to the vacuum. But if we look at the subsystem, we expect to see relaxation. Okay, from the point of view of the subsystem, we should see that the symmetry seems to be restored. And in fact, if we study, for instance, here, I'm considering a spherical disk in infinite volume. You see at the beginning, I prepare the states. Here in the vertical line is this asymmetry. On the horizontal line is time. At the beginning, there is some amount of asymmetry, but when we let the system go, it relaxes towards 0. Okay, so we observe a relaxation. Yes.
So don't you expect if this is a discrete spectrum, we can feel that there will be resurgence or something?
Well, you know, the Hamiltonian doesn't have a discrete spectrum. I mean, we're dealing with a CFT, and yes, so of course, I mean, it's not going to the vacuum, but from the point of view of the subsystem, it looks like, well, this is the result. Yes. And then, okay, you can ask other questions. For instance, so in this plot, what I'm doing is that I'm changing the subsystem size. And so the blue line is a smaller subsystem. The red line is a larger subsystem. And as expected, a larger subsystem takes more time to relax because the relaxation happens by leaking towards, I mean, from the surface, from the boundary of the subregion. So it takes more time. Here, it includes temperature. So the blue line is lower temperature. The green line is higher temperature. And you see the temperature masks somehow this asymmetry, so give you lower asymmetry, but then the relaxation time is the same. And then another, yes, let's see. So yeah, then we can ask about, so if you consider different out of equilibrium states, they can relax at different speeds. So once again, we could entertain a possibility that states in which the symmetry is broken more actually relax faster. And so what we did was to consider states that are created by operators of different dimension. So this gives different excited states. And here is the result. So you see here, what I'm varying is the dimension of the operator that creates the state. And here I have a state that breaks the symmetry less. It has a slower relaxation, and this state breaks more, and it has a faster relaxation. So this is, once again, a quantum version of this Mpemba effect, which happens generically in any CFT for these particular states. So this is the asymmetry. So in the vertical line is the asymmetry, the von Neumann one. Yeah, so this is a CFT. And I show you that the asymmetry at leading order in lambda, so this lambda is very small, is a very small perturbation on the vacuum. And in this, the result is generic, is universal. For these particular states that are created by just the identity plus lambda v. And it's valid in any CFT, in unitary CFT in any dimension. Yes, this is a disk in infinite volume. Now, what is the interpretation of this? We don't have a sharp interpretation, but you might say that if you have an operator of larger dimension, this might excite modes of higher energy, and these modes have a faster decay, and so because of that, the symmetry, they relax faster. This has been made more precise in integrable systems. So in integrable system, there is a quasi-particle description of this, the time evolution of a symmetry, and in that case, it can be made precise. The fact that there are quasi-particles of different speeds, and if they carry, depending on how you spread this asymmetry between the different modes, you can see this asymmetry due to the fact that you give this symmetry breaking to modes that are faster. Here it's less clear, but perhaps this is a physical interpretation. Okay, this concludes this part on the U1. Yes, perhaps. So we didn't explore it in detail. Yeah, I share this feeling. It should be described by maybe some shock wave in the bulk or something like that. But yeah, we didn't try to make it precise. Okay, so now in the second part, I would like to try to go from some specific symmetry, in this case it was a U1, to very general symmetries. In particular, going to this general framework of generalized symmetries and categorical symmetries, non-invertible symmetries. Try to see how we can define and perhaps compute this quantity in that framework. And this is some work to appear. Okay, so if we go back to the definition, essentially in order to define this quantity, we need to be able to define a symmetrized density matrix. Okay, so given a density matrix, we need to define a symmetrized one. Because once we have that, we can use the very same definition, either of the Reni asymmetry or the von Neumann one, by computing these traces or this log. So we need to construct an object that we can call a symmetrizer that takes a density matrix, a reduced density matrix, and spit out a symmetrized one. So how do we define it? So before going to the definition, okay, I don't have time to explain in full details, which has been worked out right now, this framework of generalized symmetries. But essentially, these generalized symmetries extend the notion of symmetry from a symmetry group to the full class of topological operators in a quantum field theory. And these topological operators, essentially, they generalize the concept of a conserved charge. They can also have different dimensions, and they are described mathematically by higher fusion categories. This structure, this mathematical structure, not only enumerates the topological operators in the theory, if you want the symmetry elements in the theory, but it's also described possible intersections between these different topological operators, possible braiding phases that you obtain when you have operators that are linked with other operators, and various types of topological moves that you have when you try to move one operator through the other, or you have networks of these operators and you do various types of moves. So in particular, they describe Toft anomalies and a lot of different phases. Now, it turns out that depending on the physical setup that you want to describe, and by physical setup, I mean the space-time dimensions in which you are, the spatial manifold that you choose to put your system in, the subsystem that you choose, then you will have a different Hilbert space that describes the subsystem in a given spatial manifold in a given dimension. The reduced density matrix will be an element of the endomorphisms of this Hilbert space. There will be some operator. And these topological operators will act on this Hilbert space, forming some algebra A. Okay? And so out of this higher fusion category, which is generic for the theory, depending on my physical setup, I will create different algebras. And depending on the different algebras, we'll have a different symmetrizer. I don't know. I don't know how to, what do you think K0 should be? Physical, sir? Okay. No, I will, in examples, I will show you what this algebra is. I mean, essentially, this algebra is the algebra of topological operators that act on the Hilbert space. Yes. So, yeah, so this algebra, if you want, is a standard algebra. There will be generators, Ka. I will restrict to finite dimensional algebras. Besides, we will be dealing with semi-simple C-star algebras. So semi-simplicity comes from the fact that we have a higher fusion category. C-star comes from the fact that I look at unitary theories. And so this algebra have a product which is described by some structure constant T. So now we want to construct the symmetrizer. And the symmetrizer should satisfy the following very obvious properties. So it should be a linear projector. We want to project this rho to a symmetrized rho. The symmetrized matrix should commute with the symmetry if it is symmetrized. If the original matrix is already commuting, then the symmetrizer shouldn't do anything. So we don't want to project too much, if you wish. And moreover, if I start with a density matrix, I should spit out a density matrix because I need to compute this, like the relative entropy. The relative entropy is defined for density matrices. So it should be trace preserving, and it should spit out something which is Hermitian and positive definite. And so, yes, so of course there is this problem. So if you consider a subregion, there is something happening at the boundary, and there is some regularization that you have to do. And I will adopt the Omorita-Chikawa regularization, in which you cut out some small disk and then you send it to 0. So in this sense, the full Hilbert space does not factorize, but you construct a map from the full Hilbert space to a factorized Hilbert space. And I will work in this framework. It's not the only possible regularization, but it's one regularization. And in that framework, yes, rho is a well-defined density matrix. Yes, let me just say, so these conditions essentially state that this should be a projector from operators to operators that commute with the symmetry. Okay, so this is just another way of saying this. And it turns out that this equation have a unique solution. The solution is very simple. So you have to act on your density matrix on the left and on the right with your generators of the algebra. And here you have to put a matrix. This matrix comes from a bilinear pairing, very natural bilinear pairing that you construct with the structure constants. If we were in Lie theory, this would be the Killing form. Okay? And then this turns out to be non-degenerate, so you can take the inverse, and this gives you this simple formula. So this simple formula is the unique solution to these axioms, and it provides this symmetrizing. All right, so now that there is this general formula, we can go and discuss some examples. And now I will focus on 2 dimensions because I want to do some explicit computations. In 2 dimensions, the symmetry in general is described by a fusion category. It's a zero-form symmetry, it's described by a fusion category. This contains 2 pieces of information. One is the fusion algebra. Essentially, the symmetry elements are topological lines, LA, and they have a fusion algebra. This fusion algebra is described by non-negative integer numbers, this n. And then there are F symbols that describe essentially the Toft anomalies in the theory. So, for instance, suppose that we are considering the full system. So we start with the circle, and the system full system, then it turns out that this algebra that I was talking about is just a fusion algebra. Because this fusion algebra tells you what you obtain if you take your topological lines and you put them on a circle and act on the Hilbert space on the circle one by one. Or equivalently, if you are dealing with a CFT, you go state operator correspondence, you take an operator, you surround it by a line, and you act with this line concentrically. Okay? This is the fusion algebra. So this K is constructed with the structure constants, which are the constants of the fusion algebra, and you use this formula, and this gives you your symmetrizer. And for instance, you can use this. So what can we ask? So an interesting question is to try to discuss spontaneous symmetry breaking. 5 minutes, okay. So suppose that I want to describe spontaneous symmetry breaking in 2 dimensions of a finite non-invertible symmetry. So can we do that? So at low energies, the system will be described by a TQFT. Okay, this TQFT will have some number of states on the circle. It will have some local operators that are the order parameters, and will describe a Hilbert space of 0 energy states. Let's say that there are n of them. Okay? Now, in principle, we could take any of these states and compute the asymmetry, construct the density matrix, and compute the asymmetry of these states. However, it turns out that there are special states that I will call vacua. These are the states that satisfy cluster decomposition. So in quantum field theory, if there are multiple 0 energy states, we are not interested in generic linear combination of them. We are interested in the ones that satisfy cluster decomposition. When you go very far distances, 2-point functions factorize into 1-point functions. And it turns out that there is a very nice categorical description of these states. I'm not going to go into the details, but essentially they are described by module categories. And these states corresponds to the simple objects in this module category. And it follows from this mathematical construction that these states form a non-negative integer valued matrix representation. So the representation of these lines that act on these states is given by negative integer numbers. Your matrices have non-negative integer entry. And these numbers follow from these module categories. So what can we do with this? Well, very concretely, consider this example. So take the tricritical Ising model. This is the next minimal model after the Ising model. It turns out that this model has various relevant operators. There is one with the specific left and right dimensions, which is interesting because it breaks the full symmetry of the tricritical Ising, but it preserves the symmetry of Ising, which is also called the Z2 Tambara-Yamagami fusion category. Now, depending on the sign of this relevant deformation, you can either flow to the Ising model or you can flow to a gapped phase. This gap spontaneously break the symmetry of the Ising model, and it gives rise to 3 vacua that I will call plus, minus, and F. And now, in fact, it has been noticed long ago by Hughes that these 3 vacua, they are degenerate because they are protected by a broken symmetry, but they do not have the same physical properties. Now, this is quite unusual. Usually, when we break an ordinary symmetry, we can have multiple vacua, but they have equivalent physical properties. These vacua do not. And for instance, we can compute the asymmetry, and in 2 of them we find some number, but in the other one we find some other number. So first of all, this asymmetry is non-zero, so it detects the fact that we are spontaneously breaking the symmetry, and also detect the fact that these states have the inequivalent physical properties. Let me also notice that these numbers are not the log of an integer. I mean, this one is, but this is the log of square root of 8. So it's no longer true that for a gapped system that spontaneously break non-invertible symmetry, you don't find the log of the number of states. You find more general numbers. Okay. And so this perhaps will be my last, because of time, last slide. Let's see. before the conclusions. So it turns out that if you have a non-invertible symmetry, the symmetries not only act on the untwisted sector, but in fact they map the untwisted sector to twisted sectors, and they can also reshuffle the twisted sectors. So there is a more general action that non-invertible symmetries have on what we can call the tube Hilbert space, which is just the sum of the untwisted Hilbert space and all the twisted Hilbert spaces. Okay, this is a much larger Hilbert space, and there is a larger action of the symmetry on this Hilbert space. And this action can be described by these pictures, in which, so this picture is a cylinder, okay? I still consider the theory on the circle, but I also consider twisted sectors. So they are described by a vertical line. This is a topological operator along time. This creates a twisted sector on the circle. And now we can act with the blue lines, which are again topological operators, but now they are horizontal along space. And so they give you action on the Hilbert space. And you can multiply these elements by putting one cylinder on top of the other and then resolving by collapsing them and resolving, and you get an algebra. Okay, so this algebra is described by some coefficients here that can be computed, and this is a more general algebra than the fusion algebra. It goes under the name of the tube algebra. And so this shows you that depending on the physical setup, the same symmetry can have different Hilbert space, it can act on different Hilbert space through different algebras. Now this there is an explicit formula for them in terms of symbols, but it's a more general algebra, it's non-abelian in general, and you can construct a symmetrizer under this full tube algebra, and you can obtain an object and a symmetry that is more powerful than the one with respect to just the fusion algebra. Just to give you an example, if you consider the spin operator in the Ising model, and you look at this state here, the spin operator that acts on the vacuum, if you use just the symmetry of Ising in the fusion algebra, this is an eigenstate, and it does not break the symmetry. But if you use the full tube algebra, this operator is mapped by Kramers-Vanier duality to the disorder operator that is usually called mu. And so they form a two-dimensional representation of the tube algebra. And so now this state does break the symmetry because it's mapped to another operator. Essentially, the untwisted sector is mapped to the twisted sector, in which you have this insertion of this twist field. And so using the tube algebra, you can detect asymmetry of this state here. Okay, so my time is over. So let me go to the conclusions. So let me conclude. So I showed you that this entanglement asymmetry is a quantum information-based observable, which is well suited to detect symmetry breaking in quantum field theories, in localized subsystems, and in out-of-equilibrium states. Let me just mention some interesting questions that are under investigation. One is how to extend the discussion to higher form symmetries, like you go in higher dimensions and you have like one form symmetries, how to define this object and compute it. I mentioned this page curve of asymmetry, and of course a very interesting question is what physics of black hole does it describe? Is it possible to obtain it from gravity? And finally, there is a question about what is the holographic formula. We had a partial answer to this question, but not a general answer yet, but we have some work in progress about this. So thank you for your attention.
Thank you very much. Questions?
Thank you. If I giving a symmetry fusion category, can you always find a system that such that the symmetry of this system is just the given symmetry fusion category?
Sorry, I didn't understand the question.
Given a symmetry fusion category, can you always find a system that such that the symmetry of this system just the given fusion category?
Well, I mean, in general, if you have a dynamical theory, you know, I'm not sure. I mean, we could expect that the answer is yes, but I mean, you need to construct it explicitly. I have in mind this example of the Hagerap fusion category, in which people were trying to construct an honest CFT that has this as a symmetry, and I don't think that people have succeeded yet. You can always construct a TQFT on which the symmetry acts, if you want, because given a fusion, like in two dimensions, when you have this fusion category, you always have the regular module category, and that describes a gap phase in which the symmetry is completely broken. So, okay, if you want a kind of trivial answer, is that as a gap system, you can do it. But as a, you know, fully interacting theory, okay, I don't know. I mean, there has been some work using the lattice by the group of Sakura Shafernameki and other people in trying to construct some lattice models that can implement either in two or three dimensions that have an action of generic fusion category or two categories. Yeah, so those are systems on the lattice. They are not relativistic theories, but perhaps in that context, the answer is yes.
More questions?
Could you maybe explain a bit again? So when you consider this perturbation as a function of delta, the asymmetry as a function of the dimension of the perturbing operator, and you made some plots, what is the intuition and what happens when you take delta to be, say, very heavy? Do you get some universality in this limit because all the heavy operators are universal? Or you showed that asymmetry grows with delta. How does it grow? What controls it? Is there any intuition why?
Well, okay, so first of all, does it increase with delta? So yeah. I consider, of course, the special class of excited states. And in these excited states, there was also a coefficient in front that was this lambda. Yeah. So as you change delta, you also have to say, what do you do with this lambda, which is dimension full? And there is also a question of what is the position of the, you know, you're going to create a state, you can insert this operator in the Euclidean past. So where do you put this insertion? Once again, the distance is dimension full. So there are three parameters if you want. And whether this asymmetry increases with the dimension, it depends also what you do with the other parameters. So yeah, I mean, we kind of played a little bit with the parameters in such a way to have this bump effect. Because if you play in a different way, sure, maybe you don't have, I mean, you can arrange such a way that you don't have it. Now, if you ask more generally, I mean, if this delta is very large, what happens? I have not looked at it. I mean, holographically, I would expect that you have a very very heavy operator, which is now dual to some geodesic in the bulk. Will not be described by a scalar field. Yes, will be described by some particle, some geodesic. It's very interesting. We have not explored it. Yeah, so I don't have anything intelligent to say.
Page curve example.
Yes.
What was the symmetry?
Yes. So they essentially they take this page model, but in which each site has multiple states. The simplest case is that there are two states at each site, and there is a U1 that acts on it. And then you have to act, I mean, you average of a random unitary that acts on it, and you create the state. And then they looked at the asymmetry of the radiation. So if you want the asymmetry of the complement. So you have this state, I mean, this randomized unitary represents a generic state of the black hole. And they want to ask, now there is black hole radiation. Can I see that the black hole is breaking the symmetry? And at the beginning, you don't see it because the symmetry is 0. So you cannot rely, you don't have enough information to say that. And when you reach the page time, then you do know that the black hole is breaking the symmetry. This will be the interpretation. You have this jump, and then, okay, then it also increases afterwards. If you collect more information, you see that actually breaks in more and more.
It's literally what Page had done. This is literally the SUN. The symmetry is the SUN symmetry. Is that right?
No, the symmetry is a U1 that acts locally. So, I mean, you have all these pins.
I see.
So each site is a two sites. You randomize with a UN for all of them, but the U1 symmetry you look at only acts locally, which is important. Exactly, this result relies on locality of the symmetry. You can do the same computation with a symmetry which is not local, and you don't get the same result. Yes, yes. But it has to be local. Yeah. In fact, they also have the computation for non-abelian symmetries, and it's the same. So it's not just U1.
Okay, I think. Thank you very much. Thank you, Francesco. See you tomorrow.